hello everyone. My name is Ioannis Tomkos. I'm a professor at the University of Patras coordinating the FlexScale project. I will talk about the X-Hole, the work we are doing in the FlexScale. So this is the scope and the overview of the presentation. I'll talk about the scope and the consortium, but then about the requirements that demand very advanced X-Hole networks to be deployed in the future. In that framework, I will talk about the main innovation areas that we're focusing on and our KPIs, primarily on multi-terabit per second transceivers and petabit scale switches that should be deployed at the optical X-Hole, alongside with developments we're working on the SDN control and streaming telemetry areas. So keep in mind that a wireless network is only as good as the fixed network it runs on, and this is the case with the X-Hole. So the consortium is here with 15 partners. It's a rather small project with 5 million budget. And this is our scope, let's say. We need to support this disaggregated run, and our particular focus is at the backhaul part of the network, while we are also having some activities related with the support of the midhaul. So at the underlying layer below the IP routers, we have the optical transport network, which consists of very high capacity switches and their interfaces that go to terabit scale today. We would like to advance the current state of the art, going to very high capacities and throughputs in the order of 10 terabits per second for the capacities of the links and petabit scale for the throughput of the nodes. The reason for that is because we all know now the emerging use cases that will be introduced with 6G as per the IMD 2025 report. So we need to be able to support all these new capabilities that 6G promises. So to do so, we consider the advancements in the wireless networks towards 6G, and at the same time, as I said before, we need to consider the evolution of the fixed networks that support them at the X-Hole. The reason why we need extremely high numbers, capacities and throughputs, as mentioned before, is because of the new services that are anticipated to be introduced at the wireless edge of the network. And considering some simple calculations, of course, based on some educated assumptions, today the capacities that need to be transported from the front haul to the rest of the network go up to several hundreds of gigabits per second, but with some assumptions about the type of services we will have in 6G and beyond. At an evolved situation, we are talking about multiple terabit per second capacities. So this is actually in line with the vision of the evolution of the transport networks in general, as defined by the SRIA Research and Innovation Agenda a couple of years ago, that indeed the predicted numbers for 25, 28, 30 are extremely large. So this is where we come and we focus our work to be able to deliver such numbers, such KPIs. Of course, within FlexScale, we don't focus just at the data plane. And I'm talking about the IP over optical transport network segment, but also we focus on the associated control plane, and in particular how we can actually develop an X-Hole transport interface with an associated SDN controller, orchestrator, and the X-Hole and packet level controllers. So this is the reference network architecture based on which we're working on. You can see here all the segments of the X-Hole, the front haul, the mid-haul, and also the backhaul. So at this network, we are trying to deploy advanced optical cross connects, which go hand with the associated IP routers at the various hierarchy levels from HL1 to HL5, aggregating the traffic and going to higher throughputs. So for this purpose, we need to develop the associated technologies, switching technologies, transmission technologies at the optical layer to be able to serve the needs. For our studies, we're considering the reference network topology, the Telefonica network, and based on this, we're conducting our studies. The studies initially are conducted based on simulations. Hopefully in the future we will be able to extend this to a digital twin of the entire network. So we are developing the associated models for all these optical X-Hall elements like transceivers, switching nodes, and so on and so forth. We are taking the inputs from the network architecture and the traffic demands that needs to be served. And based on these inputs, we hope to provide some answers as to when some technologies, new technologies needs to be deployed at the network, at which time some other technologies need to be decommissioned, and all this having in mind not just to improve the throughput of the network, but also improve the energy efficiency and security as much as possible. So the evolution so far, where we are standing with capacities per channel and throughput per link, are listed here. You can see that we have exceeded terabits per second capacities per channels and 100 terabits per second for the entire links. But now we are targeting 2030, and these numbers need to increase further. And we need to use every possible ways to scale up the capacities. So the first is to scale up the capacity of single lane, single wavelength, single I/O interface for the transceivers. Today we are at 800 and 1.2 terabit per second, and we aspire to reach 3.2 terabits per second by the end of the decade. This is the target by the Ethernet Alliance, by the way. Within the FlexScale project, so far we're proud to have demonstrated a solution that can achieve with today's commercially available components this target of the future, the 3.2 terabit per second. But of course, we need to work more on our developments to showcase the actual performance. The performance of these single channel transceivers is hindered by the fact that we need to use quite a lot of electronics and signal processing, which is costly, of course, and primarily energy consuming. So this is a major issue because we can enjoy all the benefits of having such capabilities to get higher performance signals. However, this comes, as I said, with high cost and high power consumption. Besides the DSP, we need to consider also the use of many digital to analog converters and analog to digital converters at the interfaces of the electronics with the optical components. These are the constituents of the transceivers that go into the nodes, the switching nodes of the network, and there are certain limitations currently with respect to those electronic technologies. So we are developing based on photonic devices and programmable photonics concepts, new such components, optical DACs and optical ADCs that will help us to go one step further. Of course, once you have a high capacity single channel solution, then you can use various multiplexing schemes to scale up the capacity further. So we're currently working on an approach that is called ultra-wideband. It is the well-known wavelength division multiplexing concept, but we're scaling beyond the conventional C-band, which occupies only a small portion of the available fiber bandwidth, and we can extend to very wide spectrums with our technologies beyond 6 terahertz, and 10 to 15 terahertz are within reach in a short time. So another way that we are working on to expand the capacities of these XPOL networks is using space division multiplexing. Essentially, we're talking about parallel systems at which, though, we have integrated the transceivers and also the transmission equipment alongside the fibers, the optical fibers itself. This is also a possibility. So once you consider such new multiplexing scheme to multiply by at least a number of 10 or even beyond the capacity of existing systems or the systems we hope to reach in a few years from now, you need to re-engineer the entire network. You need to develop new types of components that are relying on this space division multiplexing concept. This is actually what we are doing in FlexScale, and that enables us to achieve these numbers of the SRIA vision document that I presented up front. So as part of our innovation activities, on one hand, we're trying to scale up the capacities by taking advantage of all possible dimensions that can enable us to reach higher rates. And this is, of course, a larger number of wavelength channels, larger number of spatial lanes, advanced modulation formats, and so on and so forth. And as I said, the vision is to reach the 3.2 by the time that the 6G networks will become available, as predicted by the end of the decade. However, today's technology is limited to what it can achieve. It is limited to, let's say, at this point in time to 1.6 terabit per second, but the particular technologies that are utilized result in significant distortion and performance degradation. With the technologies we're developing within the FlexScale project on the right, that we can get signal constellations that are much more clean and achieve better performance. Of course, these transceivers, the reason to have them is to plug them in as using pluggable transceiver modules to the switches and the routers that we utilize in the IP over OTN network. And these switches today are capable of performing wavelength switching. So they are called WSSs, wavelength selective switches. And of course, we can have the possibility to use fiber switching to switch the entire fiber bandwidth. Of course, you can understand that from the granularity of switching a wavelength to the granularity of switching an entire fiber, there is a long way to go. And in between, in this evolution, we proposed and we're developing currently a entirely new type of device, which is called waveband selective switch, WBSS, that is capable of switching entire chunks of spectrum, a large number of wavelengths as a whole. Hopefully in the future, as traffic increases, we will be able to start decommissioning the conventional WSSs and deploying WBSSs. And in the far future, beyond 2030, an estimate is that we will need it by the year 2050 or so, we will not utilize any more wavelength switching because the capacities to be transported are so high that needs from that point forward to switch entire fiber capacities with the optical cross connects. So there is such a need to go beyond petabit per second throughput switches, and within FlexScale we have developed an architecture, a novel architecture, a multi-granular switching node with this waveband selective switching layer included. And by the use of it, we have estimated now with our studies that we can exceed the 10 petabit per second limit using certain size devices, WBSSs in particular. Currently, we are in the process of fabricating those devices to be tested in the third and final year of the project. These devices are based on conventional Mach-Zehnder interferometer structures that are used in optical transmitters, but are used in a certain way to create lattice filters, which are capable of carving out part of the spectrum from the optical fiber bandwidth. So with those devices, we can switch to any direction, any size of spectrum we want. And of course, that part of the spectrum can carry multiple hundreds of terabits per second. Of course, as I mentioned before, beyond the physical optical transport network with all these innovations I have discussed, we are also considering in the framework of the project the interface of this OTN network with the IP network. We're talking about a converged IP OTN where we can establish end-to-end connections across the network by passing, in some cases, the power-hungry routers and directing the traffic to the underlying optical transport network. So in that way, we can achieve much higher energy efficiency for the entire network and, of course, satisfy the evolving traffic demands, as I mentioned before, with the new capabilities we are introducing in the network. Of course, both these IP routers and the associated optical transport network equipment, the switches and the transceivers they incorporate, needs to be properly controlled. So we're working based on the TerraFlow concepts, and we follow the developments of the various standardization fora focusing on the transport network. And in particular, within our project, one goal is to develop the packet SDN controller and the optical SDN controller that associates with our new optical networking elements we are developing. And all this will be integrated in the overall network SDN network control. So with all these developments I have described at the optical layer and also at the IP over optical transport infrastructure with the associated control, we are very close to achieve with our activities the targets of SRIA, the Strategic Research and Innovation Agenda I discussed at the beginning. Key targets specified in this research agenda. You see what we are addressing with the technologies that I have described, these ultra-wideband systems utilizing also space division multiplexing and these very high capacity transceivers utilizing more and more photonic processing instead of digital electronic signal processing. And with these technologies and the novel architectures we have proposed, it seems that we can achieve the targets, and in the remaining of the project, of course, we need to showcase those developments also experimentally. So I come to the summary, and to the end of the presentation, I have described the evolving 6G network requirements, the traffic expectations that we foresee, which push the demands for the optical transport layer, and of course the IP of the optical transport network, and how all this affect the design of the X-haul, in particular the backhaul and mid-haul parts of it. The main innovations were briefly discussed, talking about new types of multi-terabit per second transceivers and petabit scale switches, as well as our efforts to integrate everything and orchestrate under an SDN control plane. With this presentation, I believe that you have an idea about what can be done at the X-haul part of the network and how optical networking technologies and photonics can assist in that effort. We're also working currently, and you will hear more about these developments in the future in other such webinars. We're working also on a new phase 2 project, which covers the front haul part of the network now. So the entire X-haul is being investigated, and hopefully we will have some really good solutions to discuss in the near future. On behalf of all the consortium partners, I would like to thank you very much for your attention. And of course, if there are any questions, I will be happy to take them.
Thank you very much for your presentation. I think in the chat we have a question that is related to the kind of transport network service models that are considered for 2030, and also what optical network elements, including pluggable and transmitter, model are considered for 2030.
Okay, so I will start with the second question. As I said, we are trying to develop these transceivers that can achieve such performance. But of course, these transceivers need to go into the pluggable modules that are plugged into the optical switches and the IP routers. There is a very wide suite of such pluggable modules that has been proposed over the past. SFP, XFP, OSPF, and OSFP, and others. At the moment, there are debates and discussions in the industry which type of such pluggable modules will prevail. The goal of this pluggable module is to make them as small as possible, size-wise, and handle the power that is required for these transceivers to operate properly. So low power, small size is the target for these pluggable modules, but in the heart of them, we're talking about the use of some advanced optoelectronic components, as I mentioned, DACs, ADCs, optical photonic modulators, which at the end needs to somehow achieve these very high capacities. So this is actually one of the topics we're working on, novel type of transceiver implementations to reach this multi-terabits per second. And the first question, I don't remember.
It was about what model you are using for transport network service.
For the services, well, for the services, in order to get such numbers discussed here, we're assuming all the type of services that can be supported by the existing and anticipated use case families. So we consider, let's say, these discussed use case families and the associated services, which of course we need to have really demanding type of services to use and assume for getting that number. So we're talking about XR, we're talking about telepresence, we're talking about digital twins, and so on and so forth. So with such assumptions, then we can actually make predictions as to the traffic that needs to be transported from the cell sites through the front haul to the rest of the network. And as I said, based on such estimates, we can get these numbers, which are dramatic. They seem dramatic, so that's why we're working to achieve with our designs that can serve those needs.
Thank you.